In Chapter 5, we are mostly focusing on quadratics. But at the beginning, I wanted to go over some vocabulary. So first, we need to understand what real roots are, or what zeros of a polynomial are. They're the place where the graph crosses the x-axis, the places. So this one has 2 real roots. This function, looking at it, has 3 real roots. If I want to see 1 real root, my graph could look like a lot of things. I'm going to draw a quadratic that just comes down and hits once. There's my 1 real root. And 4 real roots. Let's have a little fun with this. 1, 2, 3, 4, like that. 1, 2, 3, 4. All right. So real roots, where they cross the x-axis. So visually we can look. If we want to solve for the real roots, if we're solving, then we want to set the equation by setting the equation equal to 0. So you see in these 3 examples down here that we've set a quadratic equal to 0, and we were able to factor that quadratic, split it, and solve. So there are our roots. This graph would cross at -5 and at 1. For this one, you can see that the quadratic is set equal to 0, but the choice we make is to add the 2 over and then square root both sides. And don't forget, if you square root, because there was no square root in the original, if you square root, you have to put in the plus minus. So we see here again, there are 2 real roots. They're just irrational. In the 3rd example, we have a degree 3 polynomial. I know that by the highest exponent of 3. And this one is set equal to 0. And I wanted to remind you about factoring by grouping. So we look at the first 2 terms. I can take out an x squared. And if we look at the last 2 terms, I can factor out just a -1. And that becomes times x minus 2. Then remember, with grouping, we look for that common factor. Write it down. And then we write down the outsides. Oh, look, we have dots. And lo and behold, we have 3 real roots for our degree 3 polynomial. So I know that if I graphed this polynomial, if I put into my calculator y equals x cubed minus 2x squared minus x plus 2, I would see it hit or cross the x-axis at these 3 places. Now, algebraically, sometimes you can't factor. Sometimes you don't have an example like number 2 where you can just bring the constant term over. So in solving quadratics, which is what Chapter 5 is about, we're going to use 2 different methods if they can't be factored. The first is completing the square. Now, we did this with circles in Chapter 4, so this is a little bit of review. And the steps aren't perfect, so pay attention. I'm going to change or add to these just a little bit. So the first step says isolate all the x terms on one side. Let's get our x terms together on one side. And remember, I like to leave room. You want to leave room for the number you're going to be adding to complete the square. Let's take this 2 over and then balance the equation. Remember, you've got to pay attention to both sides of the equation. We'll be adding the same thing on both sides. So we find half of b and we square it. B is the coefficient of x. So we're going to take half of 4, which is 2. We're going to square it, which is 4. And we're going to add that to both sides. So plus 4 plus 4. So we've got our balanced equation. Then you need to factor the left-hand side. I left that out of the steps. You have created a perfect square trinomial, which means that these two factors are exactly the same. And in our case, it's x plus 2 and x plus 2. So we can write that as x plus 2 all squared. On the other side, just sum up your numbers. Negative 2 and 4 is 2. Then we'll square root both sides. We are square rooting. Right here, we need to do our plus and minus. You square root, you plus minus. So important. Otherwise, we won't get our 2 roots. On the left, we have x plus 2. And on the right, we have positive and negative square root of 2. Then we solve for x. I like to put this number in the front, okay? And here are our 2 roots. So our 2 roots, whoops. Our 2 roots are x equals negative 2 plus the square root of 2. And negative 2 minus the square root of 2. For the most part, you want to leave them in simplest radical form. Sometimes you'll be asked to do a decimal approximation, and those are coming up, so let's continue. Let's try another one. I would encourage you to pause the video right now. Try this one on your own, completing the square, and then come back and see if you've got it right. So I'll work through this. My x terms were already on one side alone. I need to leave some space to complete my square. Half of 6 is 3, or even you can think of negative 3, but we're always squaring it, so we'll always be adding. I hope you checked yourself. I hope you tried this one on your own. You can always put it fresh on another piece of paper and try it on your own another time. So there we go. 3 minus the square root of 7 and 3 plus the square root of 7. Okay, for example 3, it says sketch the graph and estimate the roots to the nearest tenth, then find the roots in simplest radical form. So let's see if I'm going to find my roots in simplest radical form first. So I'm going to take and set this equal to 0. Actually, get my x values alone, bring my 2 over, leave space, leave space. Half of 2 is 1, negative 1, negative 1 squared is still positive 1, always will be. Perfect square, x minus 1, it factors into. Square root both sides, plus and minus. No smiley faces this time. And solve for x. So we have x equals 1 plus radical 3, and x equals 1 minus the square root of 3. Okay, so I've got a decent x and y axis already on here. Let me put this into my calculator, so take a moment and put it into your calculator. Let me see if I can pause the video for a sec and get that up here. Okay, so I put the equation into my calculator, x squared minus 2x minus 2. I'm going to hit zoom 6, so I think my window will be pretty decent. And there's my parabola, looking good. And I'm going to actually look at the table and get some points to plot on my notes. Minimize that, and I see we have 0, negative 2, 1, negative 3, and like that. Go ahead and get some nice points so we can sketch our parabola. Okay, pause if you need a little more time. They're asking me to look at the graph and estimate the roots to the nearest tenth. So you can see I've got a root there and a root there. And the more careful you were, the closer you're going to come to a decent estimate. So looking, I can see that this is maybe about negative 0.7. And the other one, I'm going to guess, let's see, 1, 2, I'm going to guess 2.8. So these are my estimates. Now, how can I see if those estimates are close? Well, let's take our graphing calculator and actually evaluate these expressions. So type in 1 plus the square root of 3 and type in 1 minus the square root of 3. One plus the square root of 3 is 2.7. Oh, pretty good guess. And 1 minus the square root of 3, negative 0.7. I swear I didn't cheat. We can tell because our graph is decent. So these were about 2.7 and negative 0.7. Not bad. All right. A couple more examples with graphing and solving. We have, the question here says, without graphing, the parabola, describe the translation, reflection, or the scaling that must be applied to y equals x squared to obtain the graph of each given function. Now this one's going to be a little different. I'm going to use completing the square. We're not solving this one though. We are getting a new form of our parabola. And it's called vertex form. And it was also in chapter 4. I might have you go back and look at that. The vertex form of a parabola looks like y equals x minus h all squared plus k, where hk is the vertex. And the vertex is the turning point for a parabola. So I'm going to take this equation, I'm going to change it to y equals x squared minus 6x, and I'm completing the square, so I'm going to leave some space, plus 7, and then I'm going to put some space after 7. And what you're going to see me do is complete the square where I need to add a number, and then over here I'm going to subtract the number. So I'm going to add and subtract the same number from the same side, which has a net of 0. Half of negative 6 is negative 3, squared is plus 9, so I add 9 and I subtract 9. Now watch what happens. This is a perfect square trinomial, so I factor it, x minus 3, x minus 3, and this is just a number, minus 2. So I get x minus 3 all squared minus 2, and I can look and think about your transformations. This should move my parabola to the right 3 places. And this should do what? If you said move your parabola down 2 spaces, you were correct. So I know that based on an original parabola, never forget to label your axes. An original parabola, 1, 2, 3, 4. 1, 2, 3, 4. My axes are a little sloppy, I apologize. That if I grabbed this parabola and I moved it to the right 3 units, let me duplicate it. If I moved it to the right 3 units, 1, 2, 3, and down 2 units, 1, 2, that I would have my new parabola, which had this equation. Go ahead and graph that. Hopefully, you will see that that is the equation of that parabola. And what we did was used completing the square. Little bit different approach for completing the square, but it's super cool. All right, so the bell is going to ring on me. I have to hit pause. I still need to do the quadratic formula. I think I'm going to do that in a separate video. So, sayonara for now.